Good afternoon, everyone. We are Group 10, and today we are going to present the key insights from a paper title, A Tokenized Role Attribute-Based Access Control Using Smart Contract for Supply Chain Applications, also known as TRABAC. This research explores a novel method for controlling access within blockchain-based supply chain systems. The solution focuses on the integrating both role-based and attribute-based access controls using smart contracts and NFTs. My name is Nirmana, and I am presenting this work alongside my group members, Aralugaswaththa, the Silva, and Senevirathna. This paper was published at the 2021 IEEE International Conference on Blockchain, which is a highly recognized platform for state-of-the-art blockchain research. The authors include researchers from K.B.L.H, Macquarie University, and the University of Sydney. As of late 2023, this work has received over 40 citations, reflecting its growing influence in the field. The study address access control issues within decentralized supply chains, an area where traditional models fall short due to the distributed and trustless nature of blockchain environments. Modern supply chains are becoming increasingly complex, involving multiple parties such as manufacturers, logistics providers, and retailers. Each of these entities may operate on different systems with varying access needs. The paper outlines four major challenges that arise in this context. Decentralization. There are no central authority governs access. Then security and trust, where data integrity must be preserved without assuming trust between parties. Then fine-grained control, which requires decision based on more than just user roles, and interoperability, meaning the system should flexibly handle diverse access requirements. TRABAC aims to tackle these challenges through a blockchain-based solution. To address these issues, the authors define four research objectives. First, they aim to enhance security by implementing a robust and verifiable access control mechanism on the blockchain. The second, they combine role-based access control with attribute-based access control to leverage the strengths of both models, RBAC's simplicity and ABAC's flexibility. Third, they introduce tokenization using NFTs. It represents subject, objects, and actions that enabling dynamic and traceable purposes. Finally, they focus on reducing gas costs on the Ethereum blockchain by optimizing the smart contract architecture. Together, these objectives shape the foundation of TRABAC and its potential for real-world applications in supply chain systems.
Let me start by giving a quick overview of what TRABAC actually is. So TRABAC stands for Tokenized Role Attribute-Based Access Control. It's a model designed especially for supply chain applications, and it uses smart contracts to manage access control. What's interesting here is that it combines two layers of control. One is role-based access control, other is attribute-based access control. So let's now move on the first layer, RBAC. This level works by assuming user-specific role like admin, moderator, custodian, or user. Each of these roles comes with a set of permission, and only users with the appropriate role can perform certain actions. Behind the scenes, this model using many-to-many mapping between user and roles and permission. What this means, for example, one user can have multiple roles and each role can have control access to multiple functions. Once a user passes level 1 with a valid role, we then check level 2, which is where attribute-based access control or ABAC. Now, this is where TRABAC becomes more powerful. Instead of just checking what role someone has, ABAC looks at specific attributes attached to the user or the object they are trying to access. These attributes are encoded inside a special token called AGL tokens, or AGL for short. So basically, access decisions are made by comparing the token's attribute tags with access policies defined in the smart contract. This allows very fine-grained access. Let's take a closer look at how these AGL tokens are structured. Each token includes three main parts. T-type, which tell us whether it is a subject or an object token. T-tag, which is the attribute tag like inspection or warehouse. And T-meta, which hold extra metadata. This could be a JSON file, document link, or even an image. These tokens are linked to Ethereum addresses, so access checks are based on what token the user holds. All right. So now let's talk about activity tokens, which are like the dynamic layer on top of AGL tokens. These are used to record specific activities linked to the AGL token. Think of them as a log. Each AC token document an event like a transfer, a custom check, or new data entry. And since they are also stored on chain, they ensure traceability without altering the original AGL token. Each AGL token can have multiple ACs, forming a one-to-many relationship. Let's go over the roles defined in the TRABAC and what each one can do. First, we have admin role. This is the most powerful one and it can assign or revoke any other role. But interestingly, it can't perform token action. Then we have the moderator who can create subject type token, basically represent the users. The custodian can create object type token and also log related activities with AC's token. And finally, the user role is read-only. They can view token and activity record, but not change anything. These roles are strictly separated, so they are not overlapped.
Okay, then move to the methodology. The author built their prototype using industry standard blockchain development tools. They use Branch to simulate a local Ethereum blockchain with 10 test accounts. Tuffle for smart contract deployment and leverage open ziplines, audited ERC 721 and access control libraries for security. This setup allowed them to test TRABAC in a controlled environment that mirrors real blockchain conditions. This is an architecture diagram for the development stack they have been used. Let me walk you through how the author implemented level 1 access control. The moderator role assigned to address B has the exclusive ability to create subject tokens. In their experiment, the moderator creates 7 tokens with different tags like supplier, transport, and inspection. Then delegated these to various custodian and user address. Importantly, when other roles tried to create subject tokens, the system correctly blocked them with error message. This is flow diagram for the token delegation. The author implemented level 2 with fine gradient control through tokenized attributes. Custodian roles can only create object tokens that match their assigned tag. For example, address C, which hold a supplier tags, can only create object and activities with the supplier tag. The paper also introduced activity token as children of object tokens to track changes and operations. Address C created data in induction activity, while address D created transfer related activities. Now you can see the creation and access of token and activity in TRBAC. The access control validation demonstration TRBAC effectiveness. The results show that users can only access tokens and activities that match their assigned tags. Access address C and F both with supplier tag can access the supplier related tokens. Address I, despite having a valid token with warehouse tag, cannot access anything because no objects extract with that tag. Most importantly, address J, which has no token at all, is completely blocked from accessing any resources. This demonstration both positive and negative access control working correctly according to the author's design. This is an access matrix table. This is showing which address can access which tokens or activities based on text magic.
So, good afternoon, everyone. So, now today let me conclude our presentation by summarizing the main findings from our project on tokenized role-based attribute-based access control model for supply chain applications. Tokenized role attribute-based access control was designed to address the challenge of secure, fine-grained access control in complex supply chains involving multiple organizations. It achieves this by combining widely used models, namely role-based access control, which is assigns broad functions based on user's role, and then attribute-based access control, which adds the second layer of control based on specific attributes or tags. So in our implementation, we define four distinct roles, namely admin, moderator, custodian, and a user. So each role has unique non-overlapping privileges. This strict separation ensures that unauthorized parties can create, transfer, or access tokens and related activities, which is essential for maintaining data security and governance across different organizations in the supply chain. So then let's move to the next slide where I'm going to explain the experimental results. So to validate tokenized role attribute-based access control, we developed a prototype on a simulated Ethereum blockchain and tested it through 5 access control scenarios. In our experiment, shows that the system enforces both role and attribute restrictions precisely. For example, only moderator could create subject tokens and only custodian could create object tokens and associated activities. Moreover, even with these roles, users could only perform actions if their attribute tags match those required by the system. So then I'm going to explain about unauthorized attempts, such as an admin trying to create a token or custodian trying to access a token with their own tag. They were automatically blocked by the smart contract. This demonstrates that tokenized role attribute-based access control not only provides security at their role level, but also achieves fine-grained control at the attribute level, preventing privilege escalation and unauthorized data access. So then let's move to the cost analysis part, where I'm going to explain how the cost is distributed around each function. Here, every transaction on Ethereum incurs a fee measured in gas units. The complexity of the smart contract and the amount of data processed determine the gas cost. In our test, adding a moderator cost about 90,000 gas unit, while creating a new token required roughly 305,000 gas units. The very first token creation was more expensive at around 365,000 gas unit due to initialization overhead. We also observed that the length of tokens attribute tag slightly affected the cost, with each character adding about 12 gas units. These costs are predictable and scale in a manageable way, but they highlight the importance of optimizing smart contract design, especially for large-scale development. So that's it. Let's move to the conclusion and finally conclude our presentation. So in summary, our work demonstrates that tokenized role attribute-based access control is an effective and practical solution for secure access control in supply chain applications. By enforcing both role-based and attribute-based restrictions, it meets the need of multi-organization, multi-admin environments without overlapping privileges. While there are operational costs associated with smart contract execution, these can be reduced through contract optimization and efficient attribute management. For our future work, we plan to further minimize contract size and explore the use of environmental condition as additional attributes, making the system even more flexible and cost effective. So that's it. Thank you for your attention, and let's wind up the presentation.